Hello class, welcome to the tutorial video for electron configuration. Again, I'm Ma'am Nicole Ugto, and we will go through identifying an atom through electron configuration, then noble gas configuration. Okay, so first, let's just have a review about how we can identify an atom through electron configuration. So the first method would be counting the total number of electrons. So in atoms, the number of electrons is equal to the atomic number. Especially if you would look in the periodic table, you can already see the atomic number. So for us to count the total number of electrons, what we know is that these subscripts, these superscripts in the electron configuration corresponds to the number of electrons in that particular element. So for us to count that, so as you can see here, this is 2 plus 2, that's 4, plus 6, 10, plus 2, 12, plus 6, 18, plus 2, 20, plus 10, 30, plus 6, and plus 7, that's 37. So the number of electrons would be 37. So with this, since we already know the number of electrons, we can now know the atomic number of the element that we are finding. So in the periodic table, the element with an atomic number of 37 would be Rb, or rubidium. All right, so that's for that. Then the second method would be in terms of using the last electron of the atom to locate it in the periodic table. So for example, as you can see in this SPDF notation, the last electron of the atom would be the 5s1, or the electron in the 5s orbital, right? So 5s1, just keep that in mind. So if you would look in the periodic table, this is how we can actually use the periodic table in locating electrons. So the elements in this table, or in this area of the table, corresponds to these orbitals. So for example, in our example, the last electron is in 5s orbital. So that means that the element that we are finding, or we are looking for, is in this part of the periodic table. And if we would look that, or find that in the periodic table, that would correspond to rubidium, right? So 5s1 again. So 5s, right? So these are the elements in the 5s, or can accommodate electrons up to 5s1 or strontium up to 5s2. Therefore, the element that we are finding for would be rubidium. So that's for that. Now, for the noble gas configuration, we can further write the electron configuration of an atom by looking at the noble gas score. So the noble gas score just refers to the noble gas element that most nearly precedes the element being considered. So if you would take, for example, the aluminum atom, this would be its SPDF notation, as you can see here. And this is how we would write it in its orbital diagram. So just to review what we have tackled last time as to why we would write it this way, and that noble gas configuration of the aluminum atom would be, okay? Why is that so? So as you can see here, this is the SPDF notation of neon, and that if we would look at the periodic table, okay, so the example is aluminum, right? This is the aluminum atom, or the aluminum element. And that the element, or the noble gas, if we would look here, that immediately precedes aluminum would be neon, right? Neon, not argon, but neon, because argon is the noble gas element that would follow aluminum, but not the noble gas element that precedes aluminum. So with that, if we would consider the SPDF notation of neon, that would be this in our example. And then, therefore, we could use neon as a placeholder for that electron configuration. So as you can see here, we replaced this with neon. So after we write neon, or the atomic symbol of neon, that's the time that we write the remaining electrons in the configuration, which is 3s2, 3, and 3p1. Okay, so to be thorough in the steps in writing the noble gas configuration, so first step, locate the considered element in the periodic table, then identify the noble gas immediately preceded by the considered element. Then the second step would be enclose in a bracket the identified noble gas, then proceed with the SPDF notation for the remaining electrons. Use the periodic table as your guide. So for example, we have here fluorine. So as you can see here, fluorine, it says that it has the atomic number of 9, so therefore it is here. So this is fluorine. All right. So now we know where fluorine is. Then another step says that we have to locate the preceding noble gas. That wouldn't be neon, but it would be helium. All right. So when we have located the preceding noble gas, you can just write it in brackets. That would be helium. Then we just have to write the remaining electrons. So okay, so we know that helium actually has an SPDF notation of 1s2. So 1s2, this would be 2s2, right? Then this would be the 2p orbital. This is 2p1, 2p2, 2p3, 2p4. Fluorine would be 2p5. So that would be 2s2, 2p5. All right. Let me just change the color of my pen. So this would be the shortened version of the SPDF notation because we don't have to write everything. We just have to replace parts of the notation with the corresponding noble gas configuration. So if we would write the extended or the long version of the SPDF notation, that would be 1s2, 2s2, 2p5. Right? And if we would add the electrons, that would be equal to 9. So if we would write the noble gas configuration integrated to the orbital diagram would look like this. So we have 2. So this is how we properly write this. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the 2 more electrons came from the helium right here. So for the extended version of the orbital diagram, we just have to put the 1s2 here. Then that if we have filled all the orbitals, that's the only time that we would use the electron spin, the negative 1/2 electron spin. So that would be for the fluorine. So this would be the noble gas configuration. This would be the extended SPDF notation, right? And so on. Okay, so phosphorus. First, we have to locate phosphorus where it is. So for us to locate phosphorus, this would be here. And the preceding noble gas would be neon. All right. So now we can just use and put neon here. So from neon, we can now fill it in until we reach phosphorus. So this would be 3s2. Then from here, this would be 3p1, 3p2, 3p3. All right, so that would be for phosphorus. So you can pause this video for the SPDF notation or the extended SPDF notation. Okay, so for the extended SPDF notation, we just have to write everything. So that would be, so first let's start here. So that would be 1s2, then here, 2s2, then here, fill this in. So that would be 2p6, then this one, 3s2, then here, or here. So that would be 3p3. So for its orbital diagram, okay, can you fill in the orbital diagram? Okay, so this would be like this. So for this one's for 2p6, this would be for 3s2, and for 3p3. All right. So now let's go to this. So a while ago, I have told you as to how we would identify an atom based on its SPDF notation or its configuration. So first that we would do is we can count the electrons. So this would be 2 plus 2, 4 plus 6, 10 plus 2, 12, 18, 20. So 20. So this means that it is the calcium atom. But also, we can just base it here for S2. So 4s2 is, this is 1s2, 2s2, 3, 4s2, 4s. This is the second one. So 4s2, 4s1, 4s2. This would be the calcium, right? Calcium atom. So the preceding noble gas for calcium would be argon, right? So for us to write this, we just have to write argon or its chemical symbol AR, then just write the remaining electrons. So that would be 4s2. So that's just how you write for calcium. So for you can do it yourself as to how you would write the SPDF notation of calcium. So I'm challenging you to do that in your paper. So right, and also the orbital diagram for that. All right. All right. I hope that you will do that in your paper. Okay. But also for just to illustrate the orbital diagram with the integration of noble gas configuration for calcium, we would just put it like this. Right? All right. So that's for calcium. All right, so very quickly in terms of the elements that doesn't follow the Aufbau principle, because half-filled D subshells are not as stable as filled subshells, but they are more stable than other configurations. So for example, the chromium element or the chromium atom, they don't fill in the 4s1 or the 4s orbital first, but what happens is that the electrons have all uh, the electrons have all clockwise spin or clockwise electron spins. And that based on Hund's rule, the atom is more stable if the atom has more parallel electron spins. So that means that if the electron has more electrons with the same spins with them. So as you can see here, all of the electrons in the chromium atom has clockwise spin. While another exception would be the copper element as well, because filled 3D subshell is more stable than a filled 3s subshell, or 4s rather. 4s subshell. As you can see here, it didn't fill in the 4s subshell first, but it filled in the 3D subshell because what the atoms want is stability. So it will always prefer a more stable configuration. So that's all for this particular tutorial. I hope that you were able to grasp the lessons more.